Hi friends, welcome back to yet another video. This video, what I'm going to talk about is slightly different. See, this problem in one of my previous videos, I solved it, but unfortunately there was a mistake. So, couple of things I'm going to cover in this video is that first talk about the forced response of an undamped single degree of freedom system, then tell you how to solve this problem this time correctly, and tell you where I got it wrong and where you can also get it wrong when you do this kind of problems, and what is that small thing which you need to pay more attention to when you are solving force vibration problems, whether it is in a damped system or in an untapped system. So lots of things to cover. Let's start to uncover them one after the other. First, let me start with the force response of single degree of freedom undamped systems. So here I have shown a single degree of freedom system where you have a single mass and a spring of stiffness little k. This particular system is subjected to an excitation force as shown over here, e raised I omega t. I have used the exponential notation because that makes life a lot easier. Why? Because usually you can describe your harmonic excitations in this form, like f of t equal to f0 cos omega t or f0 sin omega t. These are all possible ways in which you can give harmonic excitation. The good thing about exponential is that since your system is linear, this is very important, since your system is linear, you can say that when your excitation is f0 cos omega t, the response whatever you get will be the real part of the response that you will get corresponding to this per excitation. Similarly, if you want to compute the response for this excitation f0 sin omega t, then that will be the imaginary part of the response corresponding to this excitation. This all holds true when you are dealing with a linear system. Again, let me make an assumption or make a assumption because of the fact that the system is linear. Because the system is linear, I can tell when it is subjected to an excitation of f0 e raised I omega t, then the response will be something like this. The response should also have the same frequency. So omega was the forcing frequency. Now your response should also have the same frequency. Couple of things here. This capital X, this is not a real number. This is a complex number. Then you can ask me, hey man, why the heck you should choose this number as a complex number? There is a particular reason for that. The good thing about complex numbers is that it can store information regarding both phase as well as the amplitude. Okay, so that's a good thing. So when we talk about these two things, f of t is your excitation and f of t is your excitation and x of t is your response. This x of t will be lagging, will have some phase lag with respect to f of t. So in order to capture that, this x of t will have two components. One is the amplitude and next is the phase. So when you assume x of t is equal to capital X e raised I omega t, and this x, when this x is a complex number, it can store both this information. Make sense? Now when you plug this particular expression to the this equation which governs the motion of our single degree of freedom system, see this comes from Newton's second law. I'm not going to derive it, but that's pretty straightforward. Now when I substitute little x of t equal to capital X e raised I omega t, I end up with this expression minus m omega square plus k times capital X is equal to F0. Then capital X is F0 divided by K minus M omega square. I can do a couple of more simplifications. Here, I can write the same expression in this form. So again, simplifying this particular expression, you can come here. So this quantity over here tells you what is the static deflection. It is as good as thinking that you apply a static force of F0 and then you measure the displacement felt by the mass m, that will be F0 by K, because K is the stiffness of the system, so the static deflection will be this much. Then this particular quantity, which can be thought of as an amplification factor, which tells you how much your dynamic response is in comparison with your static deflection, and it is varying with respect to your forcing frequency. Makes sense? Now next, what I would like to do is plot this particular quantity over various frequencies, various range of frequencies. So if you plot it, it will look something like this. There are a couple of interesting points from this graph. When omega is equal to 0, your amplification factor is 1. That makes sense. When omega by omega equal to omega n, that means that corresponds to your resonance condition, then this particular quantity blows off. It assumes very high values. Then as you increase your forcing frequency, as it is more than your natural frequency, the curve is on the negative side. In fact, this particular value is assuming a negative number, very high values of negative number. And then as you further increase the forcing frequency, this particular fraction decreases like this. Make sense? Now, I told you x is a complex number. So what I can do is, I can write this x as modulus of x times e raised I phi. Then I can rewrite x as capital X is equal to magnitude of x e raised I0. This is valid when omega is less than omega n. The same x is amplitude of times x times e raised I pi. Why there is an e raised I pi? Because there is a minus 1. Okay, this is applicable when omega is greater than omega n. So your phase difference or phase lag or phase lead, phase difference is 0 degree in this regime. And in this regime, it suddenly there is a jump from 0 degrees to pi or 180 degrees. Make sense? Then if that is the case, then more amplitude of the is 1 divided by omega square divided by omega n whole square, and I should put an amplitude sign over here. Now what happens if I go ahead and try drawing this particular curve? This curve will look like this. It will start from here, it will blow off, or it will imagine very high values when omega is equal to omega n. Then it will come down like this. Okay, so this is your magnitude of x. Sorry, I made a mistake. It should have been amplitude of x divided by delta static. Here also I am plotting magnitude of x divided by delta static as a function of omega. This point corresponds to omega equal to omega n. So this is the response. Okay, so this value corresponds to 1. I'm not going to the details, but usually this region is called the stiffness control region, because here you can control your uh, displacement by changing the stiffness of your system. This is a damping control region, because here the response of your system can be reduced by bringing in some damping into your system in terms of viscous dampers. And this region, it is mass control, because if you have larger inertias in this large inertia in the system, the response in this region can be further brought down. I mean, you can further reduce the displacement of the system. Now coming back to the question in our hand. Okay, before that, one more thing. So in this region, your response is in phase with the excitation, and in this regime corresponding to omega greater than omega, and your response is out of phase with respect to your excitation. Okay, that's an important point to keep in mind. So step 1 is simple, read the problem very carefully. So corresponding to this system, first calculate what will be the static deflection. Or if I had applied this 100 Newton force as a static force, what would have been the displacement? My displacement would have been this much Newton divided by this K value over here. So that will amount to something like, my delta static will amount to something like 1 divided by 30 meter. That will be 1000 divided by 30 mm. That will be, delta static will be something like 33.33 mm. Okay, so this is the static deflection, but the amplitude of the force motion is observed to be 50 mm. Good? Are you good? So now I have a question for you. Where do you think we will be operating in this curve? So in this curve, where do you think we will be operating? So first point is, we can be either here, because our dynamic response is 50 mm, which is more than your static deflection. Expected static deflection was 33.3 mm. So if you the displacement of 33.33 mm corresponds to this point, it corresponds to this point. Now you are getting 50 mm, so you are somewhere here. Make sense? Good. Oh, sorry, you could be here as well. You could be here as well, because there are two values of omega for which you can get the same amplification factor. So how you determine where you are working, whether you are working here or here? You need to compare your natural frequency with that of your excitation frequency. Your excitation frequency is something like 100 hertz. It's 100 radians per second. Then now that is not given to us. So all we have is our excitation frequency is 100 hertz. 100 radians per second, but we don't know what is omega and. Make sense? If we know, think of a scenario, if we know what is the value of omega n, then it would have been simple for us to determine in which portion of the curve it will be. But now it is not possible. So now we need to solve this equation for two possible omega n values. So how we do that? So this is the amplification ratio which we already computed. Your dynamic response amplitude is 50 mm, then your static deflection is only this much, then your amplification factor is 1.5. Good. Now this is the equation. Magnitude of your amplification factor is this much. Then since you have an amplitude symbol over here, now there are two possible solutions for this equation. One is like this and the second equation is this. First, let me go ahead and solve the first equation. This equation. First equation, if we solve, it's simply a plug and chug, nothing else. If you solve the first equation, only unknown is omega n square, and in omega n square the only unknown is mass of the system. K is not, K is 3000. It is given in the problem. Rest of it is simply a plug and chug. Once you do that math, you will get a mass of 0.1 kg. So this corresponds to a natural frequency of something like 3000 is the stiffness of the system, divided by 0.1, it is the mass. It will amount to something like 173 hertz. Okay, so now if for corresponding to this, if you compute your omega by omega n, this is less than 1 because your forcing frequency is something like 100 hertz, but your natural frequency is 173. Make sense? Sorry, the forcing frequency is 100 radians per second and our natural frequency is 173 radians per second. Then also your omega by omega n is less than 1. So the units is not hertz, it is radians per second. Now repeating the same sort of exercise for this equation, for this one, clear, because we had two equations to work with. We have two equations to work with now because of the modulus symbol. Now when we solve this, we will get little m is equal to something like 0.5 kg. That will correspond to a natural frequency of 63 radians per second. So in this case, omega by omega n is greater than 1. So here in this figure, I am summarizing the whole problem. So in our problem, we saw an amplification factor corresponding to 50 divided by 33.3. This was the amplification factor we obtained. Corresponding to this amplification factor, there can be two natural frequencies for a given forcing frequency of 100 radians per second. So the possible two natural frequencies are 173 and 63.24 radians per second. And corresponding to that, masses are m equal to 0.1 kg will correspond to this point and m equal to 0.5 kg will correspond to this point. Okay, so these are the two possible answers. I got it wrong initially, but the trick is this. When in the problem they give you an amplification factor that is more than 1, which means that the curve you are lying somewhere here, not here. When the amplification factor is more than 1, always keeping in mind that there can be two values of natural frequencies for a given forcing function. Here 100 is fixed. For a given forcing function, there can be two natural frequencies which will meet the same criteria, which will meet the criteria of the same amplification factor. Thanks for watching, and I hope you won't repeat the same mistake which I did when I did this problem the first time. So thanks for watching.